Yeah.
Oh, start the recording, Ajit.
I did.
Thank you so much, participants from various universities and friends from NC State University. It gives me immense pleasure to welcome Dr. Stefan Minner from Technical University of Munich, Germany. He's a full professor in the Department of Logistics and Management. So he did his undergrad and master studies in business administration, and his PhD is in business administration, economics, and logistics, production logistics systems. So his topic was on strategic supply chain optimization, exclusively on inventory management. He has published various articles in international journals and especially on many management journals. So before 2018, he was an editor-in-chief for OR Spectrum, and right now he is the editor-in-chief of International Journal of Production Economics. So his book on strategic supply chain management, especially on inventory, single echelon, multi-echelon and stuff, is a very famous book. And in the recent past, I think last month, I remember the list released by Stanford University. So he is one among the top 2%, the top scientist in the world. So we welcome Dr. Stefan Minner once again on behalf of Inform NCSU chapter. So today we are going to discuss the mathematical programming, especially mixed integer formulations to solve stochastic inventory problems. Many people are aware that the exact solution is based on stochastic dynamic programming, but that suffers from the curses of dimensionality. So Dr. Minner is going to give his experience and share his advice on how to formulate this problem using a data-driven approach using MIP formulations. And he's going to share some of his papers which he has published in this topic. Thanks once again and welcome all of you. Before we hand it over to Dr. Minner, I request Ajit to take a snapshot. So please, participants, if you can open your camera shutters, we will take a group picture and then we will direct it to Dr. Minner. Ajit, on your count.
Perfect. Awesome, guys. I will take the snap in 3, 2, 1. Smile. Perfect. Thank you, everyone.
Okay, Dr. Minner.
Perfect. And let me thank you, first of all, for the kind invitation to this seminar and the opportunity to share some of the research we have been doing over the years together with PhD students, and we are currently working on. And I hope you now can all see my screen.
Yes.
Feel free to interrupt me at any time, so you don't have to wait until the far end if I'm speaking too fast or something is not clear. So feel free to make it as interactive as possible. Now, as it was already said in the introduction, what I'm trying to present today is a kind of things which we are typically seeing as two parts of the world. Now, if we look into industrial engineering and operations research and operations management, at least that was the way when I learned operations research, then mixed integer linear programming or mixed integer programming was a tool for primarily deterministic problems, production planning, scheduling, or also deterministic inventory problems. Whereas for stochastic inventory problems, we were primarily using stochastic dynamic programming, Markov decision processes, and so on. And some of the work we are currently doing is actually using mixed integer programming for solving stochastic inventory problems. In particular, when it comes to feature-driven uncertainty and also using big data, but also for typical, of course, parameter setting problems. Of course, some of you might say, we all know from classes that we can also solve Markov decision processes with linear programming. So that doesn't come as such a surprise. But nevertheless, I hope that I can share some news and a little bit of a framework which also tries to integrate the tasks of stochastic modeling, forecasting, and building demand models, and do it in an integrated way with inventory level optimization. Now, as a motivation, how did we get to that topic, and how did this idea emerge? I think all of us have seen this picture in one way or the other when we talk about analytics and big data. When we say now, if we look at forecasting and in inventory and industrial engineering, we typically talk about demand forecasting. And then in the second step, we use those forecasts for decision making. So that's what we call prescriptive analytics. But typically we frame that as sequential and independent tasks. So the forecasting exercise delivers the input for the inventory optimization task. And what I will try to convince you today that this doesn't come with some issues if we do it the way we learn it from all our famous inventory textbooks. So that's to put it into perspective and also big data. Now, the second thing is if we look at inventory research and how inventory research has evolved over the times, and also when we look at forecasting, primarily we are looking into time series based forecasting, right? So we learn about moving averages, exponential smoothing, Holt-Winters method. We learn a little bit about regression and multivariate models, but now in the age of machine learning, of course, we are saying there's more, there's big data, right? So there's more patterns in demand, and there's more than just detecting those patterns from time series analysis. There's dependency on weather, on economic indicators, on some earlier indicators we might have from economy and market research. Now, how do we bring that additional knowledge into our traditional stochastic inventory models? So this is where this big data frames come from. Now, the second background in this research is actually from a retail application. So a couple of years ago, we started working with a retailer, primarily asking for decision support when doing inventory management, in particular for their perishable products. Now, the challenges here were not just that demand is non-stationary. So we have a pattern over the week. There's even an intraday pattern, whereas most of stochastic inventory theory assumes that demand is IID, right? So identically, independently distributed. Now, second challenge was when we talk about demand distribution, what we often observe in retail, and in particular, let's say bricks and mortar and food retailers, is not really demand, but rather sales, right? And the difference is whenever we are out of stock, then the demand observation is censored. So there's even a second problem where forecasting and inventory decisions are somewhat intertwined. And the third thing in particular in this application was because of price dependency and weather dependency, demands could not fully be explained from time series data. So this was a challenge we started with. And the question was, how can we deal with it? Of course, the problem for perishable inventory management wasn't that new. It has been around since the 70s, looking at optimal inventory policy structures, how to set parameters, but still in a rather stochastic way. And we were then trying to better balance also the trade-off between overstocks and understocks, and dealing with on-shelf availability with a mixed integer linear programming approach, which goes beyond what we had been doing before in news vendor or dynamic perishable inventory models. Now, as I already said, the second challenge in this project was were different prices for same product, and there is sales patterns over the day, right? And here you see typical patterns from a German retailer. So for those of you who are not aware, we don't have 24/7 opening hours. So typically it's Monday to Saturday, and then from 8 a.m. to 8 p.m., depending on the region. But here you see that demand, and particularly if you can replenish during the day, is not identically distributed. So there is these patterns, and how do we deal with dynamics? Now, traditional way in inventory theory, and this is also the way I still learned it, was decompose the problem into two parts. The first part is a deterministic dynamic demand lot sizing or ordering problem, and then we are adding a stochastic safety stock inventory problem on top. And what we are now trying to do is to integrate those things in here. Now, first, a brief recap of how we typically deal with data and demand modeling. I assume many of you have seen that. Usually, when we look at inventory management, we assume either a theoretical distribution or we integrate forecasting techniques and then look at forecast error measures to turn those into the distributional assumptions for the inventory scene. Now, in the retail application, as already said, demand also depends on exogenous factors, so not necessarily just a time series and just the error term, but there is some more to explain. And in particular, and that was also in our case, prices were fluctuating quite a lot, and there were promotions for products, but also markdowns, and sales highly correlate with other external factors. And how can we bring that together? Now, even though I just talked about retail primarily so far, there's similar projects ongoing currently in spare parts, where of course now we are saying when we look at predictive and prescriptive maintenance, and nowadays we have all these different sensor data available from machine usage, we can do a little bit more about spare parts inventories than just looking at the time series. So usage and also breakdown patterns heavily depend on historical sales, on usage, on installed base. So there's lots of exogenous information that we can use for parameterizing demand models for those spare parts. Now, the traditional way when we have a theoretical demand distribution, which is coming on top of the challenges, is we usually assume we know the distribution and we also know the parameters. And for all of you who have, let's say, tested inventory models in real-world applications, at least on some of my first attempts, I was wondering why we never get the service level we are supposed to get if we implement textbook formulas. Now, one of the reasons is, of course, we are assuming a distribution, and in the real data, it might not exactly be that distribution. Of course, the idea to work with robust and distribution-free approaches is not that new. So some of the ideas we are now using for optimizing parameters directly on historical data using linear programming somewhat borrows on ideas and is similar to what has been proposed also in robust optimization and sample average approximation-based methods in stochastic programming. The second challenge is we typically assume the parameters of the distribution are given. However, if we just have limited data available or just a sample, there's also a sampling error. And of course, this also has been detected in theory, but many textbook formulas, if you think about the famous K times sigma times square root of the lead time safety stock formula, is assuming that this sigma we are using is given for granted and it is not part of an estimation. And this integrated approach, which I'm going to share the details next, is trying to not make any distributional assumptions. So first of all, it's distribution free. It works with historical data and dependency of demand on exogenous factors. And it's also integrating the parameter estimation. So any errors we have from the estimation stuff will also enter the inventory calculation. Now, of course, empirical distributions, so use historical data, has been used in inventory theory, for example, in a paper to optimize parameters of a small as capital S policy, or in robust optimization by Berzimas and others. And forecasting techniques and measurements of forecast error is also quite popular. Now, when we estimate the distributions, typically the way we start off is either we use method of moments, so from a data set estimate the mean and the standard deviation, or if you want to do a little bit more elaborate stuff, also go for higher moments. Or if we are aware that demand depends on exogenous factors, we could use a single variate or multivariate regression. And then afterwards, we take the error measure and put it into an inventory model. Now, what's the challenge that we are facing here? When we do the estimation or decouple the estimation task from the inventory optimization task and just think of standard ordinary least squares regression, what we're assuming is there that over forecasting and under forecasting is penalized the same, right? If we square the difference between the observation and our forecast, it gets a symmetric weight in the optimization, and larger deviations are penalized more if, let's say, we square the errors. Now, at the same time, I assume everybody remembers the famous news vendor model. What are we assuming in the news vendor model or inventory models in general? We are assuming very often, if we have a high service level product, that under forecasting is much more costly and violates our service level targets than over forecasting where we have leftovers. So from the application point of view, using a symmetric and quadratic error measure is not appropriate. Of course, this also has been addressed recently and saying, yes, this is an issue, but still you can do it sequentially. But when you do the estimation task, you need to use a different loss function or different error function, which results from the application. So there's this recent work on smart predict, then optimize, which releases you from integrating the two tasks, but nevertheless is addressing the same issue here. And this is now what I want to convince you, that using mixed integer linear programming, we can actually do those two tasks together. The estimation task of a kind of price response or demand function and setting inventory targets. And the way how that works goes back to a paper we did almost 10 years ago from that retail application together with Annalena Beutel. So it's called Safety Stock Planning under Causal Demand Forecasting. So this was the first work. And since then, we have extended it in different direction. And I will talk about several of the extensions in the next paper. So this is not the most recent, but rather the fundamental idea how we started off. And the main idea, to explain it in a nutshell, is the following. What you're seeing on this picture here is a kind of sales or demand depending on different prices. Now you might wonder, why is price 0 or 1? This is, of course, is a normalized scale here for the price between the smallest and the biggest. So the smallest is the 0, the biggest is the 1, also to disguise the data we got from the retailer. And what you're seeing in the dots here is for different prices within that range, what was the demand? Now, typically, if we see such a kind of figure, and we were trained in linear regression, we would say, okay, now everybody sees the downward sloping price response function. So the larger the price we charge, the lower the demand. At the same time, we also see the errors, the error terms, so the fluctuation around a forecasted demand at a given price. And this is, let's say, just now the simplest version. Let's assume we just have a price and not other many external factors. So there have been other extensions recently, also the very famous OR paper by Bunn and Rudin, who made it a big data exercise. In our case, when we started off, it was primarily the price on top of an error term. Now, and if we decompose the task, we would first estimate the price response function here, maybe using linear regression. And then as a second step, we would look at mean squared errors or MAPE or any other forecast error measure to turn that into an estimate for the sigma for our inventory optimization. Now, our approach works differently and says, now, let's not estimate the price response function, but let's estimate and optimize an inventory level prescription based on the price. So if you see the line in the picture here, let's not say this is an average demand or the best point forecasted demand for a given price, but that's already the inventory level. Now, if we want to set this inventory as a linear function, but it doesn't necessarily have to be linear, except you want to use linear programming. So if you want to use nonlinear programming, you can also make it nonlinear or piecewise linear. But then what we can do is, for each of those observations, historically, we can, with linear programming, easily say what was the under forecast and what was the over forecast. So we don't need to look at the squared differences, but we can use the absolute differences. So use the news vendor metrics here for over forecasting and under forecasting, and penalize it right away with the underage and the overage costs. So the lost margin or the salvage value or the markdown we have to do at the end of the day. Now, how does that turn into a linear program? And now I'm coming to the second part of the title of my talk. What has it to do with linear programming and mixed integer linear programming? So what you're seeing here on this slide is a very simple linear program which does the following. Let's assume we have n demand observations, right? And then for each demand observation, historically, we are checking if we would set the inventory level here. So typically we would say this is our order up to level, capital S. And now we are explaining capital S as a weighted sum of feature dependent demand. And what you're seeing here is sum of beta times X is the same we would do in a linear regression. So X, J, I are explanatory variables. So what was the price behind each demand observation? What was the weather that day? Were there any specials that day in the store that attracted more customers on that day? So we would say now the S is not a single scalar, but the S depends on the feature data. So by that, we can incorporate differences we know between the different days, which are different from time. And if we do so here, then we can say for every day, let's assume we know what our target inventory level is. Whenever demand is smaller than Y is the leftover inventory, which we are penalizing with the holding cost here. And whenever demand is bigger, we have a shortage. So in that case here, we can compute the demand exceeding our inventory. And of course, we cannot sell more than what was demanded that day to account for the difference of sales and demand. And of course, we cannot sell more than what our target inventory level was. So what we are essentially doing here is a kind of representing the news vendor problem as a two-stage stochastic program, right? So for those of you who are in stochastic programming, will obviously see and remember we are taking a decision before uncertainty reveals. That's our target or news vendor order quantity. And now we are only detailing the news vendor order quantity not as a scalar, but as a function of corresponding exogenous factors for that day and that demand we have observed. Right? And then if we have inventories and sales available, we can penalize inventory at the holding cost and unsatisfied demand. So demand exceeding sales here at the penalty cost. And what you're seeing here, if we look at the decision variables, it's not only the sales and leftover inventory, but also those factors here. So how do we weight actually price and weather is an endogenous variable in this optimization problem. So we are solving the estimation task, but we would typically do separately and in advance of the inventory optimization. So this regression-like function here is part of the optimization. And once we have solved that optimization, then we do the inventory overage and underage calculation. So what this problem here does, it's both doing the price response function optimization. Of course, the detail, which I haven't told you yet, but probably you have seen that, is not ordinary squares, but the target is using the news vendor objective. And in regression, it's also called absolute regression. If you, let's say, just take the absolute value of over and under forecasting and penalize that asymmetrically. So this is a simple overage and underage cost stuff. Now, for the sake of time and also of focus, I don't want to show many extension models here. You can actually do the same for in-stock probability. So you can also count, doing the same exercise at the price of additional binary variables. How many times do we actually cause a stock out? Or by looking at the sales volumes to track the fill rate. So the interesting thing about this linear programming formulation here is it's quite rich in terms of extensions without fundamentally changing the mathematical requirements. And for those of you who have worked in inventory management might sometimes wonder, the model and the methods we are using are somewhat different if we have a pure cost approach, if we have a service level approach. Now, if we want to add capacity constraints, things are getting really messy because steady state distributions of inventories become quite complex. And the good thing about the mixed integer linear programming formulation here is adding a capacity constraint or doing some more bookkeeping variables which are tracking stock out, are tracking satisfied demands and other stuff is rather simple. And of course, in a pure linear program, computation times are not an issue. And as long as the data points are not exploding, or as long as we are not getting to multi-product, multi-echelon problems, computation time is not an issue at all. So this is about the philosophy. And here you see some examples how these order up to level functions would actually look like for the linear programming approach, and what would happen if we would use ordinary least squares or method of moments. In order to test that approach, we did both a case study with the real retailer demands, but we also had some randomly generated synthetic test instances to have full control over how demand is created. So really artificially create a linear price response function with some error term to observe based on the number of historical observations, and do an out of sample evaluation of the inventory performance, how this approach works compared to standard textbook method of moments and ordinary least squares methods. And what you see in this table, which is also taken from the paper, testing both non-stock out probabilities. So according to Silver's book, P1 service measure or fill rates, so P2 service measure at different levels of demand variation, so coefficient of variation of demand 0.3 or 0.5. And what you're seeing here is when we look at service levels obtained across the different methods and also look at the average inventory levels caused, then this data-driven linear programming approach achieves the service levels at much lower inventory levels. Of course, if you have a limited set of historical demand observations, like here with the 50, there is still some noise. So we do not precisely hit the service level because let's say if we just have 50 observations, there is still a lot of fluctuation. But what you are seeing on the sensitivity analysis, if we have more data for the estimation task, we are more precisely getting the service level targets here. So this was a kind of a proof of concept and then applied for the retail application. So that's in a nutshell the basics. So what has happened since then? Because it worked reasonably well without making distributional assumptions, without separating the forecasting and the inventory optimization task. So then together with another PhD student, Florian Taube, we extended this idea to a multi-product, multi-echelon setting. Now, why multi-product? In that case, the retailer was saying we could not order all the products every day. So they had typically ordering patterns that part of the assortment was replenished every day, but also part of the assortment for materials handling capacity constraints in the central warehouse were only ordered at certain days. And then the question was, what are good delivery patterns to certain stores for, on the one hand side, balancing workload in the stores for shelf handling and also in the central warehouse. So we would say this is a typical workload smoothing and order smoothing problem. But at the same time, how do we set inventory levels accounting for this pattern? And that's a challenge. So typically in inventory problems or in simple inventory problems, we somewhat relax that problem by saying, yes, the review period is given. Now, if once we decide about an ordering pattern, the review period becomes a decision variable. If we say we only order certain products every second day, then the review period is 2 days, whereas it's only 1 day if we really have a periodic daily replenishment. And the idea here was typically looking at ordering patterns or lot sizing patterns. That's what we have been doing for many decades using mixed integer linear programs. So can we build on this simple idea of news vendor ordering by using a mixed integer linear program to decide about the ordering pattern? And given the ordering pattern, use the same idea to set target inventory levels. And that not only in a single store, single product environment, but in a one warehouse, multiple store setting, where there are also workload balancing constraints or capacity constraints, both at the warehouse level and at the store level for order picking. So that it already prohibits picking and replenishing every product every day. So when I talk about ordering patterns, so what you're seeing in this picture here is you see the demand variation, and here now comes the non-stationary part, which I had advertised into play, that days of the week are quite different, and sometimes even morning, afternoon, and evening patterns are different. However, you typically observe similar patterns across weeks. And the question now for a certain product is, what is the right pattern and a robust delivery pattern for replenishing the products? Like here in this example, doing it on Tuesdays, Fridays, and Saturdays. But it could also be a different pattern. So that's now where we are bringing typical 0-1 lot sizing or ordering indicator variables together with what is the right inventory level. And the way we used mixed integer linear programming here was we were both encoding patterns as a kind of binary variable, and at the same time order quantities in each period when the pattern allows to order based on historical data. The second point here, because this is a multi-product context, is we are sharing features of so-called joint replenishment problems, where there is a major setup if a certain product is distributed on that day, and there's a minor setup cost for every delivery to a particular store. And for joint replenishment problems with deterministic dynamic demand, mixed integer programming methods have been quite popular. So we are borrowing on that, and we are adding now constraints on stable delivery patterns, warehouse and store capacity constraints. Now, for the sake of time, I don't want to explain the entire notation. So you see on the next slide, it's quite heavy in notation for, first of all, encoding the setup and the delivery pattern variables, and then also the usage of shelf space and labor. Just to give you an idea why mixed integer linear program is so powerful here. So once we have the setup cost structure and the labor and inventory cost parameters, we can again write that down as a little bit more involved mixed integer linear program here with lots of constraints. However, these constraints share common patterns of demand satisfaction now per scenario, right? So the data-driven, if you're wondering where's the data-driven part, if we have different weeks or different data for different weeks, we are now looking at a stable pattern across scenarios or across weeks in historical data, and then we are satisfying the overall demand. Of course, what we could do here is then bring in order up to level constraints. So demand fractions need to be in compliance with order up to level and order indicator constraints. And we could bring in capacity constraints, so the total workload according to the delivery pattern and according to the amount of inventory being handled, being put into the background, the back room, and being put on the shelf need to be below a certain capacity threshold. Now, this problem here is a little bit more difficult and also exactly solvable for somewhat limited instances. I will show you an example from our case study on the next slide. But nevertheless, you see here, it's not a typical stochastic inventory problem just with overage and underage cost, but it also allows to bring in lots of more real world capacity constraints here. Now, a short example, and here this is taken from this retailer project we had. So there we were looking into a retail company which is operating 66 stores. We had 18 weeks of data for the pattern. We were actually sampling 4 weeks according to a sample average approximation, and we were using it for 10 products here. So what you're seeing, and this is also something we have to admit, so you cannot run it for all the 66 stores for the 18 periods of data with the entire assortment. Of course, this is a room for lots of decomposition techniques or math heuristics. This is something we also tried, and we have some results. But let's say, sticking on the case study, what you're seeing at the bottom here is how much we could save with our method, so with the mixed integer linear programming approach, compared to a purely deterministic approach. So if we would run the same linear program with just estimation of moments, and then run the linear program for a single expected value scenario, we could do actually 30% better for the entire assortment. We also compared it to a simple genetic algorithm or a simple savings method, which is getting closer and more powerful, but still this mixed integer linear programming approach could gain 10% against a genetic algorithm and another 3.7% against the savings heuristic. So, and remember, this is discount retail. So 3.6% savings is sometimes more than their margin on the assortment. Now, last but not least, before I'm also running out of time, and I also want to leave a bit more room for discussions and maybe questions you have. Currently, we are rolling out this idea here to multi-echelon networks. And in the kind introduction, you mentioned my PhD dissertation, which was on a strategic safety stock placement. So what we are now working on is solving the problem. You might say I wasn't able to solve 20 years ago in my PhD. So now my PhDs have to solve it for me with this data-driven approach. And here again, we are following the philosophy of not making distributional assumptions, but assuming we have historical data, and now not only decide about inventory levels or delivery patterns, but now also decide about the inventory placement. Now, if I talk about inventory placement, and here there's just a simple example of a multi-echelon system of general network structure, the question would be, where do we put safety stocks? Do we keep safety stocks everywhere, or do we keep safety stocks only at the final demand level? So here, SKUs 4, 5, and 6. Or do we, in order to benefit from pooling, also put some safety stock at location number 3. Now, this has been also subject to research for decades, and over the last years, also because of scalability and powerful tools, this so-called guaranteed service approach has received quite a lot of popularity. And what it does in a nutshell is it's not only deciding about base stock inventory levels, and here in particular minimizing safety stock holding cost, and at the same time it's deciding about where do we keep safety stocks, everywhere, only at the final product level. So the inventory placement and inventory positioning is becoming part of the optimization problem. Now, traditionally, if we think in terms of the stochastic service approach, going back to Clark and Scarf in multi-echelon inventory theory, this is quite involved because it involves coupled integrals. Now, the good news about the guaranteed service approach under some, let's say, approximations or restrictive assumptions about bounded demand or internal flexibility, it boils down to a concave minimization problem under linear constraints. And here now we are coming back to linear programming. So if the constraints about where I put my inventories or my safety stocks are already linear, the only thing that is non-linear is the objective, where safety stocks, because of statistical economies of scale, are typically concave. Here in the simplest case, or if we allow for correlation and other stuff becomes non-linear. Now, what we have been doing is get rid of this non-linearity and also get rid of distributional assumptions, which we still have to make if we assume bounded demand or normally distributed demand, but do it in a data-driven way. Now, the data-driven way is the following. Let's assume we have historical demand. And now moving away from the news vendor, if we have a lead time in inventory, we are typically looking at lead time demand, because the first moment in time we can influence our inventory is today plus lead time plus review period, right? And then we have to look at the aggregate demand over the lead time, and this should be smaller than our target inventory level at a certain service level. So what we are interested in is no longer demands, but demands over the lead time. Now, in the data-driven framework, for example, if our lead time is 4 periods, it would mean we need to build aggregates of 4 consecutive demands. And for those aggregates, we can then, in the next step, actually treat that as lead time demand and compare it with base stock levels. And that's now the main idea, how we're taking the simple news vendor mixed integer linear program into the dynamic demand lead time repeated inventory system. So, and the second step is when we look at multi-echelon systems, we actually don't know what lead time we are covering. Let's say if we have a 2-stage system, it could be if we put the entire safety stock at the final level, we need to aggregate the demands from both stages. So it could be that the lead time is then not comprising 4, but rather 6 demands. And the pattern, how we do safety stock placement, then becomes a binary variable. So what is our safety stock pattern? And once we have the pattern, we can aggregate demand in order to be lead time demand, which then as a consequence sets the base stock level. This is the same we would typically do in the guaranteed service approach, where we say the base stock we are setting for each stock point needs to cover the demand over the so-called coverage period. So in a given period from incoming service time plus lead time delay up to the outgoing service time. And that's now essentially, and that looks a bit overloaded here, but it follows the same philosophy as the simple model, but now accounts for this lead time demand aggregation. Right, so here we are minimizing holding costs over the different demand scenarios and the different stages of the supply chain. Now here we are doing the bookkeeping again. So do we have inventories or shortages. And the main new thing is now we're building this coverage pattern here. So the binary variables, V here, are encoding the pattern for safety stock placement. And once we have that pattern, then we are actually building those demand aggregates D here in order to be compared with the base stock levels. Now, again, what you're seeing here is a mixed integer linear program. The base stock levels are continuous decision variables, whereas the pattern variables for safety stock placement are binary. And this is the simplest version where, of course, you could add capacity constraints or other things required to make it more realistic on top of that. Of course, this is getting more challenging computationally. So on the next slides, I have some numerical examples for simple assembly systems, two-stage, and distribution system, two-stage, where you see for the smaller problems, and if we are running that with 500 demand samples, computation times are in the range of a few minutes or fractions of a minute. Of course, if you want to run that for more stability with more samples, or if we have more feature data to come back now with, can we make it weather dependent? Can we make it workload dependent? Can we make it dependent on other exogenous factors? Computation times are somewhat getting larger. But as a proof of concept, what we can do here is not just follow standard sample average approximation, but also make it feature dependent as we did in the retail application. And then in order to leave a few more minutes for a discussion to sum up, what I was trying to convince you of is that we can in an integrated way solve the forecasting and several typical and standard inventory management problems, do it in a data-driven, so not just time series, but also use feature and exogenous data and a distribution-free way, account for those external factors, and also do a decent performance in environments where we have censored and, for example, price-dependent demand. Now, with all the enthusiasm, of course, mixed integer linear programming, as also in typical deterministic applications, sometimes doesn't scale well if we get into bigger problems. So, for example, we are now using the philosophy of this approach on the famous MSOM data set of Sean Willems, which has many real-world supply chains, including several thousand nodes over 10 and more stages. And of course, this then requires either heuristics for solving the problem or apply decomposition. So for all of you who are in decomposition and looking for challenging applications, this is definitely one. And these large-scale systems then, besides multi-echelon, of course, can also be multi-product, or nowadays, if we look at e-commerce and omni-channel retail, have multiple sales channels where we have to manage the inventory from a common pool, not even thinking or talking about returns and how to handle the inventory of returns at this stage. So that's in a nutshell the idea and the philosophy of the work we are currently doing. I wanted to share, and then I look forward to your questions or concerns you might have.
Stefan, that was an interesting talk. Thank you.
Thank you, Rea. Good to see you.
Good to see you too, yes. We had some work that is sort of still sitting in limbo doing this kind of thing for Clark and Scarf problems, which is not a data-driven take. It's very much basically emulating Riemann integration using integer programming. But one of the things in that work that surprised me greatly was that, you know, you end up with what appear to be these massive binary integer problems, which then turn out to solve surprisingly efficiently. And it seems to me that in some of these cases you're looking at, there may well be considerable additional structure in the integer programs themselves. My impression, forgive me if I'm wrong, is that you're using sort of generic solvers at the moment.
Yes, that's
But,
true. And I think I
there's
fully
some-
agree with you that sometimes using integer programming, if you build the models in a smart way, this opens a lot of room for valid inequalities.
Yeah.
And then adding those valid inequalities helps the solver to give much better relaxations when you just solve the LP relaxation. And I guess that's also what works in your case for the Clark-Scarf. So we have some other ongoing work where we do the same. So even if you code integer numbers as binaries, but you number them consecutively and make the sum of one binary being bigger at the previous one, and you purposely add those as valid inequalities, it helps tremendously cutting computation times from minutes to fractions of a second.
Yeah, these
Even though on first sight you're building a bigger model with more decision variables, but the polyhedral properties help a lot. And you're correct with your observation. In what I presented today and also what we did in those papers, we did not do that. But currently, in particular for the challenge for bigger problems, you have to gain some advantage somewhere because otherwise it's exploding too quickly. And this is definitely one of the options besides decomposition to exploit more structure.
Another sort of side discussion is, this is relevant, but much harder to do for the integer versions of the problem. But if you go back to your simple LP model, how does the dual of that problem have an interesting interpretation?
Actually, it has. I did not mention that. In the most simple version, if you write down the dual and look at the structure, the dual can be solved quite clever. Now, here, in this feature-dependent version, this is not the case. So this distorts it a little bit. But if you would say, let's take the news vendor with just demand observations as a time series exercise. And if you write that down as a stochastic program, and then you look at the dual, then the solution of the dual is almost trivial because it says the dual variables for the smallest values relate to the overage cost, and for the bigger ones to the underage cost. And if you just count how many of those observations are below and above the order up to level, the ratio of the counts is what separates the dual variable being positive or being zero. Mm-hmm. So it means the algorithm is saying if you have a data set and you order the observations, then the alpha percentile of that ordered set of demand observation is the optimal solution. So that's the obvious interpretation of the dual, which is nothing else than the news vendor ratio.
Right, and I mean, it also appears in things like, for example, continuous facility location problems, the classical thing where you have the fraction of the weight. This is pretty interesting. Thank you very much, Stefan. I'm afraid I have to cut to our faculty meeting. I would much rather talk to you, but the duty calls, alas.
Yeah, I hope we will have a chance maybe next year to talk and sit together and discuss some ongoing research.
I hope so also. I hope I can see you maybe in Innsbruck.
Yeah, let's hope for that.
Yeah.
Good to see you and have a good time. Yeah.
Thanks. Thank you very much also for doing this.
Thanks, Dr. Minner. Any questions from audience? You can unmute yourself. You can ask your questions.
Thanks. That was a fascinating talk. Just curious on what solvers you use to solve those kind of super large scale problems.
Now, currently we use Gurobi. When we started this project, we were still using Express, but currently we use Gurobi. And similar answer to the question before, we use it rather with standard settings. So we are not fine-tuning the solver options so far. And we are quite happy with the performance. But what we haven't tried is open source solvers. So what the order of magnitude would be that they would be smaller or capable of just solving smaller instances. But so far, Gurobi is quite helpful here.
Great, thank you.
Thanks, Zoe. Any other questions from anyone? Dr. Minner, one quick question from my side. In one of your papers, I've read that you compared this guaranteed service models versus stochastic service models. And you showed that guaranteed service models are giving relatively shorter total cost when compared to small total cost when compared to the stochastic service level models. Could you just give some light on that? So how that differs and why we need to still focus on guaranteed service models? I mean, this will be something outside the talk which we discussed today, but yeah.
I mean, it heavily hinges upon how you model the internal flexibility and how you penalize it with cost, right? So I'm not per se saying that the guaranteed service model is always better than the stochastic service model. It really depends on how you deal with this bounded demand. So the main advantage is, of course, you can solve bigger problems because you're requiring less accuracy of measuring and counting every internal stock out as a delay. As in reality, if you have internal delays, you can resume some of them and not everything propagates. Of course, the finding you have, if you assume this internal flexibility as a given, like many of these guaranteed service models do, or they assume a bounded demand, and as long as you're not exceeding the bound, you can optimize that. If you just then compare objective function values, of course, this gives a kind of advantage by assumption, because you get a second delivery mode almost for free or without any surcharge, which the stochastic service model doesn't have. So maybe this is related to why you're saying, why is the guaranteed service model better? It hinges upon this assumption, what is the price for this internal flexibility? Or how do I deal with this bounded demand? Now, once this is no longer the case, and you would say, I have a strict assumption, every delay would propagate, or if I model it as a dual sourcing problem, and it comes at a heavy additional cost, if I use that flexibility, then of course it might be more favorable to follow the stochastic service level approach. Because then the guaranteed service level approach would tell you, if holding inventories upstream is getting too expensive, you push everything downstream. And this might also miss the cost optimal solution of still keeping some inventory upstream and resuming some delays in between if demands are favorable.
Sir,
I hope
thanks
this
for that. But my question is like maybe. Yes. I get it. You pointed at two important assumptions, but when we have, let's say, multi-echelon systems where the demand is aggregated from the customer level to the upstream levels, it is always advisable to keep the inventory safety stocks on the upstream so that we can tackle and counterattack whatever the uncertainties we face in the downstream. So given that details, why do we need to still do this guaranteed service model to find out how much inventory we need to find in the downstream level?
Yeah, because you're decomposing the lead time, right? Even if you have inventory upstream, you're not exactly accounting for the delay. I mean, it might still have a delay. Even if you keep inventory upstream, there are still some cases where the demand still exceeds that upstream. And then the guaranteed service still assumes you will get it downstream as if there were infinite inventory upstream. So that's still an inherent assumption, which the stochastic service level model doesn't do.
Okay. I think someone has a question. Ivan, you can ask your questions. You can unmute and ask. Yes.
Okay. Hi, Dr. Minner. I'm actually not a student of NC State. I'm in Texas A&M. So I'm quite interested in your speak, so I just jumped in. And thanks for the presentation. These are very appealing topics. And actually, I recently just published a paper solving the guaranteed service model and safety stock placement, where I include the revenue, and my demand function is a function of the price and the number of the facilities in the system. So my question is, have you ever considered include revenue or transportation costs in your guaranteed service model?
No, we haven't, but I'm also aware of some other work who have included transportation cost, order smoothing. There's one group in Belgium who has extended the guaranteed service model quite a lot. We haven't done that. So we have always followed the traditional inventory objective. But of course, now saying once we move it more into the data-driven world, and if we look at retail, then of course revenue is the more appropriate objective than just cost minimization. And definitely transportation cost incorporation is quite important. That also relates to the previous question. If we say we need to speed up if we are running late in the guaranteed service model, so what is really the cost of speeding up? That has to do a lot with transportation. If I use a faster transportation mode, and then you could say this is one step getting closer and bridging the two approaches by explicitly modeling the transportation cost. But not sure what your experience was, how easy it was, because then it comes at additional constraints, and at least solving it the traditional way, it might destroy some of the properties, and then either you solve it heuristically or you're somewhat enumerating some values.
Yeah, yes, you're right. So what I'm working on now is trying to incorporate transportation cost. It is very hard. So it's very hard to characterize the transportation part. Yeah, we're trying to use some estimation for the objective function. Yeah, but definitely transportation cost, I think, yeah, it takes more time to figure it out. Thank you.
Just to extend the question from Wang, so when we add this transportation cost, shall we convert this into like an inventory routing problem maybe?
That would be a heavy extension. So when thinking about transportation costs, I thought about transportation costs between the different locations. Now, of course, if you're saying there is a truck or a vehicle serving multiple downstream locations at the same time and combine it with vehicle routing, then of course you are even bringing in more integer and combinatorial aspects.
Then getting this exact
I mean,
solution will be
what
very
we did
tedious.
with one PhD student who is close to finish is doing some kind of two-stage guaranteed service model with a combination of inventory patterns and some routing, but there we're already facing challenges. So in two-stage, so one warehouse, multiple retailer, where also some stochastic inventory work is available on inventory routing, that was already quite challenging. But in the big general networks, that's a tough exercise. And then
Yes.
the problem, then it gets purely numerical. You can do many things, but then journals tell you, oh, this is only purely numerical, right? So you don't have nice properties, no nice algorithms. It's a lot of brute force. But of course, let's say if you have good methods, or you find a clever way to combine that with reinforcement learning, so learning something about the structure of inventory placement or how routes are built, maybe this is a venue that people get excited about this.
Okay, thanks for the note. Any other questions from audience?
Yes, I actually do have a question.
Please go ahead.
Professor, how do you know that this model has actually an optimal value, optimal solution?
You mean this one here?
Yeah, for example, this one.
I mean, what you can say is whenever I would not stock anything. So if my order up to level would be 0, I would just get all the demands being penalized at the shortage cost. Right, so the zero solution is always feasible, and then the cost associated is an upper bound. So there's an obvious feasible solution, and then also there's a finite upper bound of the objective. So this then should guarantee existence of the optimal solution, not necessarily uniqueness. Now, of course, if we go for bigger problems and there is capacity constraints, then of course capacity constraints could make the problem infeasible, because you cannot guarantee service level at the same time. It might be conflicting with capacity constraints. Like in any other deterministic problem, if you create a too challenging capacity constraint, there might be not a feasible plan. But at least here, the zero solution is feasible. So for that reason, at least this simple problem always has a solution. I hope
Thank
that.
you, Professor. Yeah.
Any other questions? Okay, I think let's summarize. Thank you so much, Dr. Stefan Minner. I think it was a great experience for all of us, learning directly from you. I mean, this, I think it must be almost around 9:12 there, right? 9:12 p.m.
Yes.
So thanks for spending
No
this
problem. Thank you for the invitation.
late extended time. We are very happy to have you again with our Informs NCSU chapter. We look forward for some API session again, maybe in the spring semester. Thanks a lot.
Okay,
Thanks
perfect.
a lot, all the
Thank you.
participants.
Have a good time.
Thanks a lot, sir. Bye-bye. Have a great day.